Welcome everybody to the GSQ and UQ webinar series. Co-hosts here are Heather Sparks and Evan Marshall, and Rob Chatterjee, our presenter for the afternoon. We're lucky to have just one, so you will be fully ingrained in Rob's thinking by the end of the afternoon. The session will be recorded and will be made available over the next week or so. I would ask you to put things in the Q&A should you have comments along the way. We'll go for about 50 minutes and then there'll be a short break, and then we'll do the second half of the session. And first up, I'd just like to acknowledge country before Rob and Heather make comments. So the University of Queensland and the Geological Survey acknowledges the traditional owners and the custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and we recognise their valuable contributions to Australian and global society. So Heather, any comments before Rob?
No, thank you. That's good. I can give a bit of an introduction to Rob. We're all in for a real treat today. We've got Rob speaking to us. Rob's a principal data scientist at the Geological Survey of Queensland. He works on establishing data science programs to promote economic development by supporting explorers, minerals, and hydrocarbon resources. Rob's been with us for almost 2 years now, and before that he worked in a number of various roles, from corporate and business development to exploration project management. Please give a warm welcome to Rob as he gives his presentation today in 2 parts, and part 1 is boreholes. Thank you.
Thank you, Heather. Thank you, Nick. Hopefully everyone can hear me. I was just looking down at my battery and I realized I hadn't turned on the switch. So just bear with me 1 second while I turn that on. There we go. We won't run out of power through the presentation. Apologies for that. Okay, I'll share my presentation now. Okay, hopefully everyone can see that. Thanks very much again for the introduction. For those who don't know me, I work in data science in the GSQ. There's a lot of exciting avenues, but today I thought I'd talk about 2 areas that are quite interesting to us. Hopefully they're interesting to the audience. Please feel free to ask questions at the end, or if you have anything is pressing, write it in the chat. But let's start. Okay, so as Nick mentioned, we've got 2 parts to this presentation. First part is to do with boreholes. The second part is to do with unstructured text. So we'll start off with the boreholes. And by boreholes, I'm talking about borehole rationalization at GSQ. And before you see a picture of our exploration data center, where we warehouse a lot of boreholes that are important to the state's exploration. And unfortunately, due to physical warehousing constraints, from time to time, we have to consider letting go of some boreholes because we simply don't have room. So this is a talk about how we applied data science to that. So I have a number of things to discuss. It's outlined here. Essentially, we'll introduce a new technique for set subsampling. Hopefully, that's of interest to some people in the audience. We find it very, very interesting and a useful technique. I don't believe a lot of people have heard of it. So hopefully that's something that's going to be a good takeaway. I'll introduce how we applied it in a modeling sense and how we produce some data products. So just a quick background, we've got 2 drill core borehole warehousing facilities in Queensland, one in Brisbane called the EDC, as I mentioned, and one in Mount Isa. Both warehouses fill up from time to time, and it requires a lot of human intervention to review the boreholes that are surplus to our needs in the state's exploration strategy. So the idea of a rationalization program is trying to make room for physical room for more boreholes that are more aligned with our state's exploration strategy. So the image on the left is a picture of all the boreholes. They're pictured as dots on a page, essentially, that we hold in Brisbane, in Queensland. And when these borehole rationalization programs have taken place in the past by human subject matter experts, they have to consider a lot of important geological criteria, as well as the proximity and density of the positioning of those boreholes. And as you can see, we've got some areas that are very, very highly densely confined, and other places where there are fewer boreholes around. So there are potential for surplus boreholes through a program like this. So that's what we're trying to identify. So the idea of this exercise is not to replace the geologist, but to augment the geologist's ability to accelerate the rationalization process. It's a very laborious, time-consuming job. They have to consider a number of geological criteria, as I'll mention, and we wanted to provide some tools that allow them to do their job a little bit quicker. And, should it be something that was well received, could be used in future exercises. So some of the geological criteria that have been used in the past, and this goes back to the early 90s, as obviously the areas of high drilling density require fewer holes, arguably. Obviously, it depends on geology, but in general, that's something. Sorry, I jumped ahead there. The borehole length was important, and the sample of taken from the borehole important. So that was a consideration. Holes that are important to the stratigraphy, strat holes, they're considered very important. Obviously, boreholes with better core recovery are favoured over boreholes that are not so well, not so competent. And geologic age, if a borehole intersects older rock units, that was deemed to be more important than a borehole that just scrapes the surface and young rocks. And of course, the age of the borehole can affect the condition it's in the warehouse. So older boreholes can weather and disintegrate over time, and so the conditions, fortunately, are considered better in the newer boreholes. And obviously, there's a great body of work done around certain boreholes. They're published in journals and research reports, and we strive to retain that information as much as possible. So going back to the problem we were facing, is essentially we had to thin out the number of boreholes on this map based on not only proximity, but also the geological criteria that I mentioned. And so it was proposed that data science could be a a tool to help with this problem. But after quite a bit of thought, we found that standard data science methods, machine learning methods, simply wouldn't work. So classification, clustering didn't really help us, and we had to kind of think out of the box a little bit. So an idea came to me, and this is through my PhD at the SMI. I came across this journal article. It's a fantastic paper many years ago, and it sort of stayed in the back of my mind. It's essentially introducing an idea called the core set, which is a way to distill a big data set into its essence, if you will. And then if you were to apply machine learning algorithms to the smaller core set, you can achieve results that are similar to the big data set. So I thought that was always a really interesting concept. And so when this problem came about, it came back into my head, and I thought, how might we apply this? So just a quick background before we dive into that. I'll give you a background where the core sets or the technique came from. And it emerged from combinatorial and computational geometry. They're quite esoteric fields, but it's sort of branched now into statistics and machine learning. They've become popular in big data and massive data applications. So where it's very expensive to run machine learning algorithms on the entire data set, these are very helpful techniques to apply. As I mentioned, it's essentially a data summary tool. So you can subsample very large data sets and keep their essence or their information. And obviously, by reducing down the size of the data set that you apply machine learning to, you can accelerate performance, you can and achieve results without sacrificing too much accuracy. And that's a really nice thing about this method. It's a statistical method, and it provides some statistical guarantees, unlike a black box model that just outputs something. So essentially, if you can perform clustering or other kinds of machine learning algorithms like k-means or Gaussian mixtures, then you can apply the same algorithm to the core set subsample. And that accelerates computation, and you don't lose too much. So we've been experimenting with this for about a year, and as a way to address this physical warehousing constraint that we face. And so the idea of a core set from an academic viewpoint came out of some pretty famous schools like MIT, Caltech, and ETH Zurich. It then was taken up from a statistical point of view, where people applied really rigorous asymptotic and mathematical proofs to provide guarantees to the results. So as I said, you can be fairly confident that you're distilling the essence of the data set through this technique. Then people have been applying it to deep learning. Time series data is particularly amenable to this method, as I'll talk about in a second. And so relating to the paper that I spoke about before, this PhD from Caltech really inspired me during my PhD, and it's by one of the co-authors of the paper I spoke about, Matt Faulkner, and it's to do with earthquake prediction, and in particular harnessing communities' smartphone accelerometer data to predict earthquakes. And as you can see down here in this picture from the thesis, shows that the damage zone over the city Port-au-Prince in Haiti after the 2010 earthquake. You can see the different colors of damage spread across the city. And so what Matt was trying to do was provide a way to help emergency services predict where the damage will be, and to be able to, predict and essentially get a few extra minutes up their sleeve to help out people in these very, very serious earthquakes. And so this image taken from his thesis is a picture of community accelerometer data in the Long Beach, California area during the Carson earthquake. And the red is the high acceleration values, and the blue are the low acceleration values. And you can see there's quite a disparity in accelerometer peaks, acceleration peaks rather. You can actually see a fault here. So if you're in emergency services, you could perhaps expect to find a lot of emergency calls along this fault zone, for instance. Highways, interestingly, are very noisy, and so they can be a bit of a distraction. But essentially, a tool like this that harnesses people's smartphones be a very, very useful service to the community. And I think it was a great initiative, but it presented a technical problem. If you get a certain percentage of the population's accelerometer data on their smartphones, you start to build up a very, very big data set. So how do you run prediction on so much data, so much time series data? And this is where the core set came into play. They applied a core set that allowed people to predict or contribute to the prediction of earthquakes on their smartphones on the client side, which is a really cool idea. And so, as I've discussed, a core set is a weighted subset or a distillation of a large data set, and allows you to apply an algorithm, like a machine learning algorithm, and basically achieve a constant factor approximation to the result that you get on the full data. So on the left here is, imagine a high dimensional data set. It's a bit hard to imagine a high dimensional data set, but people kind of try to represent it in 3D like this, with lots of little humps, and the little blue dots under here represent those subpopulations in the high dimensional data set. They're taking the density here, so they're trying to approximate the probability distribution of this data set. If you take a small sample called a core set, you can get away with fewer of these blue dots, but you note that there are these green cuboids that need to be considered to weight the smaller data set blue dots differently among the core set data. So this is the idea of weighting, which is a key consideration I'll discuss. It was a really nice property core sets allowed us to tackle our problem. So how does core set subsampling work? Well, it works in high dimensions, as I explained, but it also works in 2 dimensions where we have a lot of dots on a page that we need to thin out. And we can include weights. But just generally, this is a really exaggerated example. If you can imagine any data set, there'd be some natural groupings that you could break away into clusters, if you will. This is some natural groupings. And if you cluster them, like here in the center, then you can associate each of those clusters with a central point, a centroid to the cluster. And then based on that centroid respective to the particular cluster, we can develop a relationship between the points in that cluster and the centroid. So we can develop what we call a sampling distribution based on its a point's distance away from that centroid. And that's shown by these colors here. And that's key to the statistical sampling process. So we sample based on the relationship in there. But the really nice thing, as I was saying, those green cuboids I was talking about, we can weight points differently. We can bias certain points to favor their sampling selection more than others. And that was key to including our geological criteria, as I'll discuss here. So going back to those requirements, we had proximity, and I proposed that proximity subsampling could be achieved through the core set algorithm. We wanted to retain as much of the borehole as possible, where we had data for the number of pallets. We use that as a proxy. So each borehole's physical footprint in a warehouse was a proxy for its length. We collect a list of strat holes, stratigraphic descriptive boreholes, and we can exclude them just by taking them out of the consideration for the algorithm at the start. For recovery, unfortunately, due to the history of some of the data in the database, we didn't have full ability to introduce that criteria, so it wasn't available, but we were able to proxy geological age by the total depth of the hole, because not all the boreholes were logged consistently, so we had to just rely on a deeper hole was more likely to touch an older rock. And of course, age of the borehole, we can take the year, whether it's the rig release date or the start drilling date or one of those. And obviously, all of the important and highly visited boreholes at the EDC are compiled as a list by the EDC, and they are excluded from the start as well. So we weren't able to include core recovery. We were able to get length, geologic age, and age as our criteria. The strat holes were excluded from the outset, and research holes as well. And the proximity is handled by the core set algorithm. So the next step was to ask, how do we encode these criteria numerically into an algorithm, which I'll get to in a second. So the way we modeled core sets was to use an available Git repo by Borsos. It's a great repo because it has a lot of examples that you can try to replicate the results that they have on the repo so that you know it's working. It really got us off to a great start. It's a little bit fiddly. We had to change a few files around in the temporary directories, etc. But we got it working, and we were able to pretty quickly apply the core set algorithm to our data. The main advantage, obviously, of automating this kind of thing through Python or another programming language was that it just saves a lot of subject matter expert time if it did its job. And so that was our ultimate goal. And we, like a lot of people in the audience, would use Python and did this in Jupyter Notebooks. Really like Jupyter Notebooks because it's just a very interactive way of programming. And we did this on the AWS cloud platform where we're quite heavy AWS users here at GSQ. So if you look at the CSG boreholes, or coal seam gas boreholes that we started with, they were considered the best borehole purpose group to look at because they have a significant footprint and they were highly densely drilled in certain parts. So particularly, in these basins like Bowen and Surat, they were very, very concentrated, so that they were a good target. But that was a little bit too broad a brush. We needed to zoom in a little bit. So we found that by zooming in at the borehole field level. So that's a borehole that retains a common name like Jurassic 1, Jurassic 2, Jurassic 3, for example. We use regular expression to find those borehole field names. And a borehole field might look like something like this on the right. There's a number of boreholes, but you can see some groups there within that borehole field. And so the way the core set algorithm works, you first perform clustering. So you can either use Gaussian mixtures or k-means. We used k-means because we wanted hard clusters. We didn't want overlap in our clusters. So you can see there are some very nicely defined clusters within the borehole field. And we determine the number of clusters by a method. It's a heuristic method called the elbow method, which essentially allows us to pick and automate the number of clusters that should exist in borehole field. So then we perform core set subsampling. Here on the right, you can see the red circles are the core set subsamples. And the size of the circle dictates the core set weight. And essentially in this context, it's the disposal pre-selection weight. So it's if a subject matter expert was to look at this, they should consider the bigger red circles first. Doesn't mean to say that those boreholes are definitely candidates for disposal. The geologist always decides, but this tool just helps them draw their eye to the ones that might stand out first for pre-selection to speed things up. And if you zoom in, this is what it might look like. One cluster of that borehole field. So we create little data frames for each of the borehole fields. And as you can see here, we've got a common borehole name. We know how many pallets are associated with that borehole, so we know that the footprint in the warehouse. And then we have these weights columns, and that's a numerical encoding of those geological criteria. But I haven't discussed how we actually came to determine those. So let me quickly discuss that. The way we encoded geological criteria into this model numerically was through a field called, excuse me, multi-criteria analysis. Essentially, it's a sub-branch of operations research or decision analysis, and it allows complex interacting criteria to be determined and encoded numerically. And if you look at Dean 2022 or any decision analysis or multi-criteria analysis textbook, it goes into quite a lot of detail. But essentially, we applied a very simple application of this. So we wanted to convert those three criteria: the number of pallets, the total depth, and the age of the hole, as numerical weight. So within a borehole field, we basically just use this method here. It's essentially placing that borehole particular criteria relative to the other boreholes in the field. So is it above average? Is it below average? And then we apply a weight, and this weighting coefficient, this coefficient, it's not the weight, is determined by trial and error. But in decision analysis, this is a number that's often referred to as the utility, and that can be facilitated through workshops, and a lot of stakeholders can come in and interact and negotiate those values, and there's actual field involved doing that, facilitating those numbers. But in this case, we just used a trial and error method to determine this, and then we inputted them into an equation here, which is essentially a very simple weighted additive model. If you refer to this reference here, it's one of the basic ways to encode weights and coefficients, but you can go into more detail, but for our purposes, this was fine. So this was a way of encoding those weights into the core set algorithm. And if I go back one slide, we arrive at these numbers, and allows to bias certain points in favor of their disposal versus others based on the geological criteria. It's quite a nifty way of doing it. So the two data products that we delivered, one was an interactive map based on those Python images that I showed you in the notebook. Allows subject matter experts to zoom around the state and focus in on particular pre-selected recommendations. Scroll their mouse pointer over the borehole and come up with some information that helps them make their decisions. And the second product is a ranked list of boreholes, and this is based on the core set weighting basically the size of the red circle, and that's not just within the borehole field. So we take all the boreholes from all the fields, put them all together, and then we just sort out the biggest red circles to the smallest red circles. And the subject matter experts basically look at the top and go to the bottom to make their rationalization decisions. So the interactive map looks a bit like this. What you see here is the CSG boreholes that I showed earlier. Overlaying on top of that, we can portray the footprint in the warehouse, the number of pallets. Here, the green circles represent the number of pallets for a particular borehole greater than 2, and then overlay the disposal ranking of the core set weight on those particular boreholes. And this is for all of the borehole fields together. So this is actually doing what we set out to do. It is helping us to thin out the density boreholes. You can see it's picking some holes more than others. That selection depends on the formula, depends on the weighting and those coefficients. So there's some experimentation into that at the moment, but it is a methodology that is proving to be quite helpful. And as you can see, this is an example of the interactive map where we can hover over a point. It'll bring up the relative information. So a subject matter expert can quickly compare nearby points and say, well, I disagree with that selection. I'll keep that recommended disposal hole. And then this is the ranked list that we provide to the EDC and to our Mules team, where I've de-identified some of the data here, but essentially you can get an idea that it shows the lat and long, the borehole ID, the core set weights, and the number of pallets or the pallet yield. So we can look at, through an exercise running this once, we can see how many pallets we are able to clear based on these criteria, which is helpful from a management point of view. But it also gives us a relative weighting of boreholes that might be competing in terms of, or there may be some warehousing constraints that prevent particular boreholes from being moved or disposed of. We might say, well, let's skip this one, go to another one, for instance. There's some final remarks. Core set subsampling is actually going to be quite a helpful way. It's demonstrated some potential to help us rationalize our storage of boreholes at GSQ. It's very much a geologist in the loop tool. It's not something that we all run through an automated approach without human intervention. And it requires constant feedback, because essentially what we're doing, we're sampling geology, which is complex. Everyone knows that. There's anisotropy. There's different rock units that there's faults and other kinds of things that we need to consider in those boreholes that we simply can't just by those basic criteria. So that's where a geologist comes in. But we'll continue to work on this to refine it, to help us continue to rationalize our storage of boreholes. So that's the first part. Nick, did you want to have a minute or something like that?
Nick just had to duck off, unfortunately, just at the moment, Rob, but I'm here.
Okay.
I guess at this juncture, if there are any questions here and now about that first part of Rob's presentation, happy for them to be keyed straight in, and we can answer them here and now. Otherwise, we are going to have the Q&A at the end of the presentation as well. Heather, I can see your camera's on now. Did you want to add anything further?
Yeah, I was just trying to have a quick look to see if anybody put any questions in.
Not as yet, I can see.
Okay.
Great.
Yeah, wonderful. I think Rob's really highlighted some interesting work that we've been doing here at the GSQ. So,
actually, Heather, I do have a question. This is from Ben Ruck. In the rationalization process, what kind of metadata are retained?
Sorry, I don't quite understand.
I might give Ben a little bit more time. Maybe he can put a little bit more description around that question, and we can come back to it if you like.
The record of the borehole remains. It's just the physical footprint, I guess.
Yeah. I've just got a note here from Matt Greenwood that all metadata will be retained. So I'm hoping that answers Ben's question.
Yeah.
Great. Okay. All right. Just checking. Yeah, no other questions at this point. Yeah, how are you feeling? Ready to kick on to part B, Rob?
Part B, yes. Great, thanks.
Yeah. Excellent. Okay, I'll hand back to you.
Okay, so in the second part, we're looking at unstructured text. And earlier in the year, we undertook a proof of concept applying generative AI to unlock insights from our online, publicly available collection of exploration reports. And the image you see here is what we imagine. This is actually a Gen AI generated image. We've got an AI that's in a library, and you ask it a question, it'll go and find the information you look for. This is essentially what we're trying to do here in this proof of concept. I thought I'd present some interesting results from that. Okay, so this is the outline of this part of the presentation. I'll talk about what we did, why we did it, what was our objective, scope, how do we make it safe, how does a digital librarian even work, what was its general architecture for those who are interested. I'll provide some example outputs and talk about a novel feature we were able to build into the model, and discuss some of the benefits. Hopefully there'll be some questions. Excellent. So as I discussed, we investigated the opportunity of applying generative AI and large language models to our custodial exploration report data, particularly related to critical minerals. And as many people in the audience know, they're key to the state's economic industrial growth, facilitating the net zero transition. They're also key to Queensland's strategy and particularly to the GSQ's strategy for the future exploration in Queensland. And if you're not aware, they're scattered all across the state. But there's a large concentration around Mount Isa, but certainly up and down the coast as well. And so by critical mineral, I'm talking about things like cobalt, copper, vanadium, etc. So we have about 100,000 digitized exploration reports available on our GSQ Open Data portal. These have been digitized very recently. A lot of work was undertaken prior to my coming to the GSQ to get those online and available to the public. It's a great resource, but currently we can only perform keyword and metadata search on those reports currently. And we thought, well, wouldn't it be great if we could apply some sort of AI, some sort of natural language semantic search capability to really converse with those reports and to connect dots between different reports on the database. So through this proof of concept, we essentially asked two questions. Can large language models, generative AI, extract novel insights relating to critical minerals exploration and do that through a conversational format? And by doing so, can it outperform previous attempts at applying some machine learning methods like deep learning transformer models? You may have heard of BERT and those kinds of models to extract insights from the reports. So our scope, it was quite small. This is not even a pilot. In government terminology, it's a proof of concept where we run a short burst of activity and did a bit of ad hoc post POC development, and that was it. We were very fortunate to be funded by Amazon Web Services. They provided $4,000 in credits for this. They also provided in-person coaching for our team. So this is the team involved in building this. We've got my offsite is Stephen Bowden, who's giving the next webinar, I believe. He was key. We also had Disha Kalal and Devendra Kumar, who are data scientists and engineers. Unfortunately, Devendra's left our team now, but this gentleman here is Ankit Patira from AWS, and he's a member of the global generative AI laboratory, and they go around the world to help clients. He's a public sector specialist, so he came and helped us build this from scratch with the help of his local solutions architect, David Hutchinson. So it was a really exciting and fun project. We contained the proof of concept to fewer than 3,000 critical minerals reports. So not a lot of data, but it allowed us to be nimble and to build things quickly. And we leveraged the AWS cloud platform. As I mentioned, we're heavy users of AWS, and we're able to apply large language models available on AWS Bedrock within AWS Cloud to do this work. And so before we set out and excuse me one second. Acknowledging that there is some issues with the state of AI and generative AI at the moment in terms of producing truthful and reliable answers. We applied some security and governance risk assessments just so that we could safeguard this exercise with a view to the application. So this is a private proof of concept that was limited to our team within GSQ, and I think there was only maybe a handful of people outside of our team and GSQ proper that were able to access this. We applied some basic security controls like user IP whitelisting, security keys. We had a basic user disclaimer. This was fit for purpose for the POC, and we were also comforted by the fact that this was an opportunity to apply the large language models available and vetted by not only AWS on their platform, but the developers. In this case, we used Anthropic's Claude algorithm. And so this was something that comforted us, the fact that that model has been extensively tested for bias, harmful and explicit content. We also undertook a couple of governance reviews. One was internal in the Department of Resources through a what they call a resources architecture group review, which is quite intensive, and then the Greater Queensland Government Fast AI risk assessment review. So how does a digital librarian work? Well, I don't know when the last time many of you went to a physical library. It wasn't so long ago for me, but certainly when you wanting to seek information about a particular topic, a librarian is very helpful. Failing that, there's usually like an online catalog or something like that you can access information for. But if you imagine the way a digital librarian works, it's very analogous to the way a physical librarian or a human librarian work. You could approach a physical librarian, ask for a particular topic. They'll tell you where in the library, which shelf, where to go. Well, a digital librarian does a very similar thing, bases it on a different system, whereas the traditional library might be based on the geodecimal system. A digital librarian, it bases its search system on mathematics and vectors. So how does it do that? Well, a user, rather than speaking to a librarian, will type a query into a chat interface. That query is then converted to vector, and it's matched to the collection of reports in our library that have also been converted to vector. But instead of converting the entire reports, we vectorize chunks of the reports or parts of the reports. That's a technical limitation of the algorithms at the moment. But essentially what happens then is the algorithm is able to match by vector similarity the user query to parts in the library that are also similar, and then pull those out as relevant references, convert them back to text, and then send them to a very powerful large language model for a coherent summarization. And this is called a retrieval augmented generation model. So why did we choose a retrieval augmented generation model? It was actually recommended by Amazon. They suggested this is the safest way to extract reliable information from generative AI currently. Obviously, this is a very fast evolving field, but certainly that was our experience. It was quite good in its way of limiting hallucinations and generating factually correct results. So essentially the way it works is, as I mentioned, a user types a query, it gets converted to vector through a process called embedding, and as does that collection of reports that we were studying in the POC. They get stored in a vector database, which I call the library, and then an algorithm mathematically compares the similarity of those chunks of the reports in the library to the user query's vector equivalent. The algorithm then pulls out the top relevant references. So it could be top 300, it can be top 50. That number is kind of variable. It depends on the algorithm's limitations, and a thing called the context window, which is essentially how much text can you throw at a large language model. So by playing with this, you can affect the number of times you can go around and ask questions. So essentially, this list of relevant references get summarized by the large language model and then sent back to the user. And the user has a choice then to stop or to then ask another question, a follow-on question, and all of that context, history of the conversation gets brought into the next query. And you can imagine this slowly accumulates what they call the tokens, the allowable text that you can throw at an LLM, and over time it will start to choke out the constraint, maximum limit for text input to the large language model. So you have to play around with that a little bit, but and it depends on the algorithm, but essentially that's the way it works. And the way we implemented our architecture was to use the AWS Titan model for embedding. Now, this is it's kind of a black box to us. We don't know. It's a proprietary AWS model, but I suspect it's got a deep learning engine underneath the hood, and that's a black box. And I would urge people to be very careful of deep learning algorithms related to my research at the SMI. I'd say that you need to be careful that the application or the test data that you're applying an algorithm to with a deep learning algorithm needs to be similar to the training data. So in our case, you could question, well, would exploration reports be part of the training set in AWS Titan? Probably not. So there may be some, degradation in the performance of its embedding, essentially. But the other thing that was important is as a way to store the library, and that's through a cosine similarity schema. Cosine similarity is just a mathematical comparison tool for comparing semantic or vector relationships. And we use as I mentioned, the Anthropic Claude 2 and 3, and found them both to be very good, but 3 was significantly better than 2 and gave a little bit more context window, so we could send more text to it. And this is something that's being developed all the time. I think that Claude 3.5 has 1 million token context windows, so that's almost 5 times as much text that you can throw at it, or at least it's getting bigger and bigger all the time. So this is a fast-moving field, but you can get the general idea. So these are some example PSC outputs. So we felt we produced an interactive tool that provides some insightful summaries across reports in our collection, not just on one report. And this could be around a prospect, a target commodity, or a geological region. And that memory function bit to engage in a conversation was quite interesting. You can see it here on the left. Here I've asked a question off the cuff. Can you tell me about the mineralogy of vanadium, mineralization in northern Queensland with a view to geomet and beneficiation? And it's it's come back, and bear in mind, this is related to a very small subset of reports. It has no idea of geology. It hasn't been trained in any geoscience texts or anything like that, but it's come back with this quite, coherent, cogent response that references a number of company reports. These are actually hyperlinks. You can click on the response to verify that statement, and it'll take you to the Open Data Portal where that report exists. But you can see it's been able to identify different mineralogy between weathered and unweathered zones. It's talking about size fractions here, for instance, which is interesting, and an alkaline leaching processing method, which is part of GeoMet. So that's something that I thought was quite interesting. And here you might ask a really general question: how does cobalt associate with pathology around various deposits in Mount Isa? And based on its very small collection, it's come back and said, well, based on these data, I can tell you that it's relating to copper ore bodies, away from the copper mineralization and alteration zones, related to ISCG, which is good to know. And muscovite schist, cobaltites mentioned, some nickel laterite, cobalt laterite deposits as well. So that's kind of a interesting answer. When you consider the previous best we could do was just search for cobalt in a search function. And here's one that's a bit more academic about a geological region, where I've asked, tell me about the stratigraphy of the Eromanga Basin. Don't know much about it. I know there's a lot of published work about it. It hasn't referenced any of that, but you could include that information one day into a tool like this. But based on just its small collection of reports, it's able to provide us quite insightful summary, talking about the different stages of transgressive and regressive sedimentation. So, oops, jumped a slides there, sorry. So one of the novel features we built into this concept architecture was the ability to search based on spatial metadata. Normally, a large language model isn't very good in handling location data, but we're able to include the location metadata into the vector index, included as attributes within the vector index. And that was through the help of AWS. It's something that I don't believe has been done anywhere. And so what it did was allow us to search and ask questions about reports that are specifically confined to a geographical bounding box, like you see here on the left. So some of the benefits of the digital librarian, well, I haven't mentioned our previous efforts using deep learning models that we performed about a year ago. I can attest, just trust me, it really outperformed. I mean, the performance was an order of magnitude or two better. It was really much, much better. It was able to synthesize disparate pieces of information, so not just one report and information within that report. It could bring multiple reports, as you saw in some of those examples, together and then provide a cogent output on over the top. It can perform spatial search, which is novel. It has that ability to converse on a topic of interest. And we found this as a useful tool to accelerate information discovery. In fact, one of our senior geoscientists, who's quite knowledgeable about stratigraphy, was able to find an ironstone unit that was previously undiscovered in the Eromanga Basin, which could potentially host cobalt, which is really kind of cool. That just demonstrates, the serendipity of using something like this. You could find something very, very interesting, whether it's for exploration or academic purposes. And we're actually reviewing its potential to help us remediate our internal geoscientific database, GeoProps. It's a legacy database that's sort of morphed from database to database over the years. There are a few issues here and there in that, and we consider that there may be some sterilized information in these reports that we can use and extract to help us remediate parts of GeoProps. So that's something we're looking at quite closely. So some of the reflections and learnings of this exercise were that we, more on the technical side, the prompt design, which is a prompt is an instruction that you give to the large language model what to look for, and the size of the chunk, the amount of the report that was broken up, were important factors in affecting the result or search quality. Unlike some researchers who found that the large language model in the augmented generation step or summarization step wasn't important, we found that made a difference. Wasn't huge going from Claude 2 to Claude 3, but certainly was very noticeable. And we were really impressed at how well it was able to just cut through some of the geoscientific jargon without any real, well, we weren't really privy to its training set, but we presume there wasn't a great deal of geoscience material in its training set. So we were quite impressed by that. I spoke about this conflict between extracting a lot of relevant references, but then that if you keep a lot of relevant references, it chews up some of the context window available in the large language model. So kind of constrains how many times you can ask questions. It affects the length of the conversation, but that's obviously something that's being extended just through technological development at the moment. Very fast moving field. I would urge people, if there are people interested in applying this kind of thing to their own data, to take a second look at the embedding and indexing processes. I think they're overlooked in terms of their effect on the retrieval step. I personally would like to spend some time looking at those. And we are aware that this was quite a successful proof of concept for a very small data set. We're considering the challenges of increasing the size of the library, say from 3,000 to 10,000 to 50,000 reports. If you think of a user's query converted to vector as a needle, if you will, in a haystack, where the haystack's the library. Currently, we have a single haystack, but what happens if our library becomes 3 haystacks, a barn full of hay, or 3 barns full of hay? Then obviously there's going to be some challenges in efficiently and effectively searching for that vector and getting the relevant references from that very large data set library. So that's an ongoing challenge that we're considering moving forward. And obviously, some people may not be aware of a particular model that's coming out at the moment. It's available at the moment, but it's still fairly much in its infancy. It's called a multimodal model. Essentially, what it does is it allows the algorithm to simultaneously look at different data modes. So, for instance, a multimodal model could look at text simultaneously with an image like a map, simultaneously with a table of data. That sounds like something a geoscientist would do regularly, looking at these reports. So I'm quite excited by the prospect of a multimodal model being able to simultaneously make inferences and provide input on those very different data sets intelligently. So that's about all I have today, but thank you very much for listening all the way through if you're still there, and I might take some questions if there are any.
Great presentation, Rob. Thank you very much. I think in a moment we're going to try promoting those who are still on the call to be panelists so they can speak directly with you. But perhaps I might give Nick a moment just to do some of that admin. And I know Ben's added another question. He posed a couple of questions to you earlier. Another follow-up question for you. Thanking you for your talk. Very interesting. What sort of recommendations do you have to select an embedding and indexing? How would you go about measuring the effectiveness of the LLM output?
Yeah, they're great questions. I don't think there's a definitive answer for that. I think in terms of evaluation of LLMs, there's a lot of work going on in this area. I think there are technologies that can automatically evaluate large language model outputs, which may be counter to what people think is the correct thing to do. But there are AIs that can check other AIs. That's one approach. We have a panel of subject matter experts who review the responses in detail. We baseline it against an internally available version of ChatGPT. That's one way we compare the responses and that way we can see whether the algorithm is adding value. In terms of embedding, that's a really good question. I haven't thought a lot about it, but I'd say that you could bring a lot of the deep learning literature into that investigation. So if you were to investigate that, I'd set up an experimental program around not a black box model perhaps, but maybe an open version of those models. So I know another group that's doing the embedding using Colbert. I think it's an open transform model, so they could investigate the effects of embedding that way. Experiment, run an experiment on different vector index schemas based on similarity. It's only one. So and the relationship of converting a vector into high dimensional space and how that relates to the way it's stored, which is also a high dimensional process. So that's something I'd look at. Hopefully that answers the question.
Yeah, great. I'm not sure if you've seen Ben, but Nick has promoted you, so you do have the ability to speak with Rob directly if you like. But we're going to add a few more people to that list as well. So by all means, please use the Q&A function, and if you'd like to speak, we'll work through bringing more people on board to talk directly with Rob, if that's okay.
Yep. So I've promoted everybody to panelist. Some people have declined, but just remember to take yourself off mute.
Sure. A question here from Vincent Fazio. Is it very expensive, Rob?
No, not very at all. But yes, I mean, if that was sarcastic, yes. But imagine what you could do with it some investment.
My word. I might just give a little plug while we're waiting for the questions to come through. So we do have another webinar at the end of October. Steve Bowden, as Rob alluded to, will be giving that presentation, and his talk is on subterranean syntax, envisaging a machine-readable Earth. So that one's on Thursday, the 31st of October. So another fascinating presentation from the Geoscience information team. So great to have Steve on board to give that talk, in a month's time.
can I add to that, Evan? I think
Yeah, go.
Steve's very interested in the application of knowledge graphs to generative AI. So it's one area where we're quite interested in grounding the response of generative AI in fact, because currently when it responds, it's simply sampling from some really esoteric high dimensional distribution based on its training data. So by incorporating a knowledge graph, and Steve's really into that, and it will be a really fascinating presentation. I think that's an emerging field. I know Amazon and a number of tech companies are moving in that direction. So it's really, really cutting edge.
Yeah, great. Okay. We don't have any more questions at this stage, but we'll keep the conversation going. Sorry, I think I cut someone off there. Sonia?
No.
No?
May more tanong off. No.
Okay. Okay. You might just mute your mic if you don't have a question, if that's okay. We do have one here from an anonymous attendee. Sorry, what is a knowledge graph in layman's terms?
A knowledge graph is it's a good question. How do I explain this? It's a hierarchical way of presenting knowledge. So if you think about a table, this table that I'm presenting on, you'd say, well, it's furniture. Furniture is something that's, creation of a human, at a greater level, or wood, table, something like that. So it's probably not the best example, but it's just a logical way of structuring data. So in terms of geology, you may be familiar with a vocabulary. So a vocabulary is a defined way of presenting geoscience information, or any kind of information, to be honest. But you start with a rock, and then you go at different scales down. So there'll be different classes of rocks. There'll be ages of rocks and that kind of thing. So it essentially provides a tree of knowledge to a large language model that allows it to sort of search along the graph where it's factual.
Okay. Yeah, makes sense to me. So I'm glad someone else also asked that question. At this point, I might share my screen just quickly, Rob, if that's okay.
Sure.
Just to give a plug for an event that we have coming up here at the GSQ. Is that displaying on screen? The Digging Deeper slide, can everyone see that?
Yes, that's fine.
Great, thank you. So for those who are unaware, the Geological Survey presents an annual conference at the end of each year called Digging Deeper. And this year, the Digging Deeper conference is taking place on Thursday, the 21st of November. So that'll be a series of presentations largely presented by the GSQ staff, as well as some of our key collaborators. It's free to attend. It's happening in the CBD in Brisbane. And in the top right-hand corner is a QR code, which will take you straight through to the registration page. As well as the day of talks, we've also got 3 workshops. So on the Wednesday beforehand, we've got a minerals systems workshop out at the core library that Rob alluded to earlier, where we'll have some fantastic deposits on display and some wonderful core viewing opportunities. So that's on the Wednesday beforehand. And then on the Friday at the end of the week, so on the 22nd, we've got 2 other workshops. One is on Northeast Queensland geophysics, and the second one is on geoscience information. So all of those workshops and the Digging Deeper conference itself, free to attend. Registrations are open now, and scan that QR code if you'd like to secure your seat. Thank you. can't see too many more questions coming through, and it looks as though those who have been promoted to a panelist are happy just to not raise any questions, which is absolutely fine. So we might just wait a few more moments, and if there's nothing else, we can wrap this up. But yeah, I've got nothing further at this stage, so just checking that I'm not missing anybody. No, it doesn't look like it. Nick, are you happy for me to close?
Yes, thank you very much indeed. And thank you everybody for joining, and especially Rob and our colleagues at the GSQ. Thank you.
Thanks so much, everyone. Bye.
Thank you.
See you later. Bye.